Okay, let's dive right into this explainer. Today, we're locking down your top band in Cambridge Additional Math. Seriously, our main goal here is keeping the examiner's red pen far, far away from your paper. We're tackling 020 differentiation for the IGCSE and O-Level 0606 syllabus, and we're going to break down exactly how to conquer this absolutely crucial topic. So Isaac Newton famously invented calculus to calculate planetary orbits, right? Standing on the shoulders of giants, as he put it. But how does his whole apple falling from a tree moment get you top marks? Well, your immediate high-stakes problem isn't tracking the orbit of Saturn. It's using his brilliant invention to completely crush your 0606 exam. And that's exactly what we're going to focus on today. Okay, here's our roadmap to ace this topic. Number 1, the differentiation rule. 2, finding stationary points. 3, tangents and normals. 4, the big 3 rules. And finally, number 5, exam strategy and pitfalls. Moving right into it, Section 1, the differentiation rule, mastering the gradient function. We're starting with the absolute foundation of calculus here. And honestly, it's a massive shift from rough estimation to perfect precision. Instead of drawing those kind of inaccurate tangent lines with a ruler and just hoping your eyes don't deceive you, we find the gradient function. You'll usually see this written as dy by dx or f prime of x. Think of this derived function as a master key. It calculates the exact, perfect mathematical slope at literally any general point xy on your curve. So the whole thing hinges on this core mathematical rule. For any function y equals k times x to the power of n, its derivative, dy by dx, equals n times k times x to the power of n minus 1. In plain English, you just multiply by the power of x, and then you reduce that power by exactly 1. That's it. And remember, differentiating any standalone constant, like, say, y equals 4, just gives 0. It literally vanishes. And if you have a massive equation with a bunch of sums and differences, don't panic. Just take a breath and differentiate each part separately. All right, Section 2, finding stationary points, maximums, minimums, and inflections. Now look, this is where students consistently bleed marks. Take a look at the flawed approach on the left. You find where dy by dx equals 0, you get an x value, maybe you assume it's a maximum from a quick sketch, and you stop. The examiner's red pen strikes hard here. You absolutely cannot just assume a turning point's nature without proving it mathematically. The flawless answer on the right shows exactly what Cambridge demands. You find where dy by dx equals 0, and then you actually calculate the second derivative, d squared y over dx squared, to rigorously prove its exact nature. And this brilliantly illustrates that flawless method. To quote the core logic directly, at a stationary point, if d squared y over dx squared is less than 0, it's a maximum. If it's greater than 0, it's a minimum. You have to use the second derivative test to lock in those final justification marks. Oh, and a quick pro tip. If your second derivative is exactly 0, the test is inconclusive. If that happens, you actually have to check the gradients just slightly to the left and right of your point. Let's break this cognitive overload down into 3 simple, repeatable steps so you never drop a mark on a stationary point question again. Step 1, differentiate your equation to find dy by dx. Step 2, set dy by dx to 0 and solve for x to pinpoint the exact location. And step 3, find your second derivative, plug in that x value, and classify it. It's an unbreakable framework for exam success. But wait, before we get too comfortable, I really need to warn you about a massive trap lurking in trigonometry differentiation. I'm going to show you an examiner clue that completely changes your answer for trig functions in just a minute. It catches thousands of students out every single year. But first, let's secure our standard geometry marks. Let's look at Section 3, tangents and normals, the perpendicular trap. Remember, at the end of the day, tangents and normals are simply straight lines. So we get to use our trusty standard straight line equation, y minus y1 equals m times x minus x1, provided we get the gradients perfectly right. But a super common pitfall is mixing up your line types when you're under pressure. The tangent gradient, m1, is simply your dy by dx calculated at that specific coordinate. But your normal gradient, m2, that's the negative reciprocal, -1 divided by m1. Why? Because the normal is mathematically perpendicular to the tangent, and perpendicular gradients always multiply to give -1. Always double check which line the question is actually asking for. Moving to Section 4, the big 3 rules: chain, product, and quotient. Okay, before we start combining functions, you need to know the derivatives of these specific types. Literally, grab a screenshot of this table right now. Notice how e to the x delightfully just remains e to the x, by far the easiest one, and natural log of x becomes 1 over x. But here is that massive trap I warned you about a minute ago. When you're differentiating any trig function, sine, cosine, or tangent, your angle absolutely must be in radians, no exceptions. If your calculator is sitting in degrees during the exam, the red pen comes out immediately and all your subsequent marks are gone. Once you know the basics, you have to identify the structure of the problem. Are there two distinct x terms being multiplied together? You've got to use the product rule. U times dv by dx plus v times du by dx. Are they divided? That's the quotient rule. V times du by dx minus u times dv by dx, all over v squared. Or is it a function nested inside another, like a function of a function? That's when you deploy the chain rule. Multiply the derivative of the outside by the derivative of the inside. Recognizing the structure instantly, that's the real secret to finishing on time. And finally, Section 5, Exam Strategy and Pitfalls, the high-stakes scenario. So let's test your mark scheme thinking with a classic high-stakes Cambridge rates of change scenario. Imagine a sphere's radius is increasing at 0.1 meters per second. How do you find the exact rate the volume is increasing? When you see a phrase like rate of increase connecting volume, radius, and time, what mathematical rule should immediately jump into your mind? You guessed it, it's the chain rule. You just follow this precise framework to connect the changing radius directly to the changing volume, and you effortlessly steal back those marks. Step 1, write down the volume formula for a sphere. Step 2, differentiate it to find dv by dr. Step 3, construct your chain rule, linking the rates, so dv by dt equals dv by dr multiplied by dr by dt. And step 4, substitute your known rate of 0.1 and solve. It really is a beautiful, logical flow of mathematics. Now you know the math. We've built your theoretical framework, and we've exposed the traps. But what if exam timing pressure makes you freeze on the actual day? Because let's be real, none of this flawless logic matters if the clock runs out before you finish your calculations and secure that grade. Look, calculus isn't just a set of arbitrary hurdles to jump through for a grade. It's literally the fundamental mathematical language of a changing universe. By mastering the gradient function, proving your stationary points, and respecting the big three rules, you completely remove the guesswork and replace it with absolute proof. The examiner's red pen won't stand a chance. So what does this all mean for your revision today? Which of these rules are you going to master first?